So finishing up Chapter 9, Sections 9.7 and 9.8, you're going to be looking at complex numbers. And complex numbers involve the use of the imaginary unit. Now, the imaginary unit, which is always denoted with this lowercase I, is the number whose square is equal to -1. That's why we call this an imaginary unit, because we've already said that the square root of -1 is not a real number. So typically the way we define the imaginary unit is such that I squared is equal to -1. We'll use that very frequently. Or that I is equal to the square root of -1. So that means anytime we have a negative underneath the radical, like what we're seeing right here, this will not give us a real number, but we can write this in terms of the imaginary unit. And basically what we do in that case is we write it as a product of a times -1. And then we're able to break up that square root, and the square root of -1 is equal to the imaginary unit I. Now, I talked with you about this before, about when you pull things out of the square root. I typically like to bring mine out in front, and that's very commonly done with the use of I, because you want to make sure that you note that the I is not under the radical sign anymore. So typically what's more common here is anytime you have the square root of a negative number, you rewrite this pulling an I out in front, and then whatever's underneath that square root is now a positive number. And then you're able to evaluate that square root or simplify that square root from there. So we're going to start out here just writing things using the imaginary unit. All right, so again, what I want to remember is that anytime I have a square root with a negative number underneath it, I'm going to rewrite this as I times the square root, and I'm going to change whatever's underneath that square root to positive. Now, because what's under the square root is now positive, I can evaluate that. Right, the square root of 25 is 5. And then a lot of times we treat I almost like a variable, and so instead of writing this as I times 5, we would write this as 5I. All right, so I'm going to quickly run through these others. Again, the same process here. If there's a negative underneath the square root, I'm going to pull the I out. That's the square root of -1. I'm going to change what's underneath the radical to positive. I'm going to evaluate if I can. The square root of 100 is 10. And this would be written as 10I. Now, if we don't have a perfect square, we can still use this to simplify. So the square root of -20, I would pull the I out in front. Leave what's underneath the square root as positive. 20 is not a perfect square, but using our method for simplifying that we learned back towards the beginning of Chapter 9, I can write the square root of 20 as the square root of 4 times 5. And then I can say, well, the square root of 4 is 2. And I'm going to pull that out here with the I. And so this would simplify to 2 times I, and the 5 would be all that's left underneath that square root. All right, and then lastly, make sure you note this only applies to a negative underneath the square root. So if there's a negative out in front, like what you're seeing here, then remember that just tells you they want the negative square root, which means that negative just tags along out in front. So the square root of -50 would be written I times the square root of +50. 50 is not a perfect square. Notice I'm just going to keep that negative out in front. So I'm going to rewrite this as 25 times 2. And then I'm going to say, well, the square root of 25 is 5. I'm going to pull that out here with the I, so this becomes -5I. And then the 2 is left underneath that square root. All right, so again, basically anytime we see the negative underneath the square root, we pull the I out in front, and then we work through it as a positive square root. Now, I mentioned when I started this section that we were going to be looking at complex numbers. complex numbers are numbers that have a real portion and a portion that uses the imaginary unit. So in general, complex numbers are written in the form a plus bi, where I is the imaginary unit. Now, we refer to A, the part without the imaginary unit, as the real part, and we refer to B, right, the part with the imaginary unit, as you might guess, as the imaginary part of the number. Now, notice if B is equal to 0, right, that means technically there is no imaginary part to that number. And so in that case, what we would have is actually a real number. Right? Like, for example, if you had 2 plus 0i, well, that's just 2, all right, which is a real number. If a is equal to 0, that means there's no real portion to the number. And so in that case, we would say what we have here is solely an imaginary number because it does not contain a real part. So let's first look at some examples of complex numbers and just identify what is the real part and what is the imaginary part. Now, the real part of a complex number is the part that does not contain the imaginary unit. All right, so in this first example right here, the real part of my number would be this entire first part, which is negative 12 over 10. Now, if I can simplify the real part, I want to do that. Right, both of those are divisible by 2, and so I'm going to state the real part of this number as negative 6 over 5. Now, the imaginary part of this number is the entire part of the number that contains the imaginary unit. Now remember, when you have a number in the denominator, it has to stay underneath each part of the numerator. Another thing to think about is if I were going to write this separately, I would have to write it as negative 12 over 10 plus the square root of 6i over 10 as well, because remember, when you add, you keep a common denominator. So that means my imaginary part is going to be this entire term here, which contains the imaginary unit. So I'm going to write the imaginary part of my number here as the square root of 6 times I over 10. Right, we're just splitting up what's the real part, what's the imaginary part. All right, so in this example below, and again, if it helps when you have a number in the denominator, start out by breaking this up into 2 separate fractions, right? Just writing each one over the common denominator. And then it should be pretty straightforward to see the real part. All right, the part with no imaginary unit would be 5/3. And the imaginary part, right, over here, would be the 2i over 3. Now, it is important to note that you take the negative with the imaginary part if it's there. So, for example, over here, this 4 minus 2i, I would state the real portion of this number as 4. I would state the imaginary portion of this number as negative 2i. So when we say a complex number is written as a plus bi, that means if there's a minus in there, that negative applies to the imaginary unit. And then don't forget, some numbers may only have one of these, right? For example, our last one here, there is no real part to that. Now, when I say there's no real part to that, it really just means the real part is equal to 0. So notice I could write this as 0 plus negative square root of 3 times I. And so when I'm just looking at an imaginary number, what that means is that the real part is equal to 0. And then, of course, the imaginary part would be the entire term with the imaginary unit, which is negative 3, negative square root of 3 times I. Now, once you can identify the real part and the imaginary part of a complex number, you can actually use this to solve equations. And all you do is you keep in mind if two complex numbers are equal to each other, then their real parts must be equal and their imaginary parts must be equal. All right, so anytime I want to solve an equation, that's what I'm going to do. All right, I'm going to set the real parts equal to each other, and I'm going to set the imaginary parts equal to each other, and then I'm going to solve for my variables. All right, so in my first example here, the real parts of the complex numbers, right, those are the parts that do not contain the imaginary unit. So I've got a 14x, and I've got an 18 over 5. So the real parts must be equal to each other. Now, if I set those two things equal to each other, I have a basic linear equation. If I want to solve for x, I would divide both sides by 14, right? That's the same thing as multiplying by the reciprocal. And so by looking at the real parts, I would determine that x is equal to, and I'm going to go ahead and do a little simplifying here. 18 divided by 2 is 9. 14 divided by 2 is 7. So across the top, I'd have 9 times 1 is 9. And across the bottom, I would have 5 times 7. And this would tell me that x is equal to 9 over 35. Now, I've got a y in there as well, so I'm going to go back now, and I'm going to take the imaginary parts, including their signs, and I'm going to set those equal to each other as well. All right, so if I set the imaginary parts equal to each other, I've got the square root of 5 times I, and then over here, I have 5y times I. Now, when you set the imaginary parts equal to each other, the imaginary units are going to divide out, so those are going to be gone. And I'm going to be looking at the square root of 5 is equal to 5y. And then if I want to solve this for y, I'm going to divide both sides by 5. And by looking at the imaginary parts, I'm going to see that the square root of 5 over 5 is equal to the value of y. And so anytime you want to solve an equation that has complex numbers, this is what you can do. You can set the real parts equal to each other, and you can set the imaginary parts equal to each other, even if you have multiple real and imaginary parts. All right, so for example, in our next equation, my real parts over here would be the 4 and the 17x. On the other side, my real part is only the negative 6. So if I take 4 positive 17x and set this equal to the other real part of negative 6, then I can solve. So this is going to become 17x is equal to negative 10 if I subtract the 4. Or x is equal to negative 10 over 17. All right, now the imaginary parts, right, the parts with the imaginary unit, including their sign, would be my negative 8i, over here my negative 20i, plus 9yi. So again, setting those equal, I've got negative 8i is equal to negative 20i plus 9y times I. Now again, when you set these two things equal to each other, the imaginary units, those are going to divide out because they're present in each term. And so my equation would be negative 8 is equal to negative 20 plus 9y, and then I can solve. All right, if I add 20 to both sides, I'm going to be looking at a positive 12 is equal to 9y, and then divide both sides by 9, and I would have 12 over 9 is equal to y, or if we reduce that fraction, dividing top and bottom by 3, I would get that y is equal to 4/3.